Most diagrams show here as one box. Your application sends something in, intelligence happens, then an answer comes out. And honestly, for Cloud AI, that picture works, right? Because you open ChatGPT or Claude, choose a model name from a drop-down and everything works fine. That's because the cloud abstracts a lot from us, and we pay for that abstraction one way or the other, right? We pay through exorbitant subscriptions, insane usage fees, limits, or dependence on the provider keeping the service available. Local AI changes that arrangement, right? The intelligence moves onto hardware we control, but the layers hidden inside that black box move with it. So for a lot of people making that switch, that is where most of the confusion begins, because the cloud trains us to treat several different things as one thing. With local AI, you often hear words like parameters, weight, base models, instruct models, GGF, quantizations, context windows, KB cache, runtime, backend, agent, and even an S, right? You don't need to master all of them at once, so there is no need to fret, right? I think that there are two gaps to cross, which is the hardware gap and the knowledge gap. And the hardware gap is, can your machine carry the workload? And then the knowledge gap is, can you see which part of the stack is doing what, right? So by the end of this video, I hope that you should be able to tell whether a term describes the file, the software, the machine, or the workflow around it. So let's start at the bottom row. Everything starts with the model. We can think of a model as a photograph, right? Saved on your computer. Once you download it, right, it is idle. But if you open it, an application loads it into the working memory and uses compute to display the information of that photograph. So for the rest of this series, right, you want to think of a model as an asset on disk that needs compatible software and enough hardware to run. A runtime loads the model before inference, but the model shares memory with your operating system, applications, context, right, cache, and temporary calculation. So file size alone does not tell you the full runtime requirement. So for a beginner, right, hardware comes down to two concerns: memory and compute. Memory determines what can fit into your system. Compute and memory bandwidth help determine how fast it runs. On many machines, right, system RAM and GPU VRAM, right, they are separate pools. But Apple Silicon uses unified memory, which lets the CPU and GPU access the same pool. Generally, more memory gives the model and the rest of your computer more room to work. My safe default has always been a recent Apple Silicon, an M2, M3, M4, M5. Those are good, right? With at least 32 GB of RAM. That is because the machine has to carry the model and everything running around it. Now that we know what carries the file, let us look at the file itself. In our metaphor, the model is the photograph, a stored asset, not the complete application around it. The model contains learning information that lets it perform a kind of task. People sometimes call the model the system brain or its learned memory. The model is not the interface, the API, the application, or agent. It is one layer inside the complete system. Inside of it are parameters, right, including numerical values called weights, which are adjusted during training. So when you see something like 4 billion parameters, that describes the raw scale of that length set. Make no mistake though, the parameter is not a universal quality score, right? So that means that a larger model may handle more complexity, but it asks more from the machine and can still be wrong for your job. A smaller task-specific model may be more useful. Size may mean parameter count, file size, or runtime memory. Those measurements are related, but they are not interchangeable. The task determines the model, not the other way around. A common place to find models is Hugging Face, right? Repositories there can include weights, configurations, a tokenizer, documentations are variant, but you still have to choose the file your task and runtime expect. Now, let's look at the file we should call the model itself. A photograph may be saved as a PNG, JPEG, or RAW file. It's still an image, but the format changes how its information is packaged and which software can open it. So GGUF is one model format commonly used by GGML-based engines such as Yaml CPP. Other ecosystems use formats and packaging such as Safe Tensors or MLX repository. So just as not every image application can open every image format, not every AI runtime can open every model format. The file and the software have to agree. Then let's get to quantization. Think of this like the resolution of the photograph, right? So the clearer version carries more detail, but the file is larger and asks more from the machine. The lighter weight version is easier to store and run, but it may lose some detail. So that is the lay of the land with Q8 and Q4. So Q8 generally retains more numerical detail and uses more memory. Q4 is smaller and easier to fit with a greater chance of quality loss. Technically, right, quantization changes the numerical position of the model's existing weight, but the useful rule is this: higher number, generally clearer and larger; lower number, generally lighter with less retained detail. Format tells the software how to read a file. Quantization tells you which size and quality trade-off that copy of the model makes. A photograph file needs a compatible application to open it. So also, a model file needs a compatible runtime, also called an inference engine, to load it. manage memory, process an input, and produce an output. So this is where names such as YAML, CP, MLS, and other specialized engines appear. In a metaphor, right, the model is the photograph file, the runtime is the application that opens it. Underneath the runtime is the backend, which is the part it uses to reach the hardware. That might be Meta on Apple Silicon, CUDA on NVIDIA, or Vulkan, we have ROCm, or a CPU part generally, right, depending on the stack. The runtime executes the model, the backend connects the execution to the hardware. So this also explains the life cycle, right, which is downloading puts the model file on your disk, loading prepares it in working memory, inference is the moment it processes an input, unloading releases the memory again. So downloaded does not mean that it is loaded, loaded does not mean that it is currently inferring. So same file, different state. Once the file and runtimes are compatible, the next question is what was this model built to do? So not every model is an LLM. There are large language models, vision models, speech models, embedding models, classifiers, and many specialized models in between. So even inside one model family, you see different variants, right? A base language model is trained to continue patterns in text, and a short model has been further adapted to follow requests. A tokenizer converts text into token units the model processes, right? So a chat template arranges messages in the exact structure that a particular instruct model expects. So those pieces need to match the model variant. You must also see things like TensorShape, which describe how the model values are arranged across dimensions. Again, none of these labels is a universal score, right? So together, these details tell you what the model can do and what it expects around it. So that is why the family name alone is not enough. You still need to read the specific variant and its model card on Hugging Face. So the right question is never just, is this a good model? It is this the right model for the job and this machine that I'm using when it comes to local hair, right? A model and what it can see right now are different things. The model weight stays fixed during normal inference, right? The context changes from one request to another, which is why we talk about things like context window. And the context window is what the model can see for the current request. That includes your instructions, conversations history, retrieve documents, tool description, and the answer being generated. So language models process that material as tokens, small unit of text, right? Models come with different maximum context length. That is the model setting. So it is not a promise that your device can use all of it comfortably, even though it fits. Yeah, you have to understand that part. So longer context usually grows the KB cache. So available memory, runtime, support, and model architecture determine how much context is practical on your machine. More context consumes more memory. It can also bury useful instruction inside irrelevant material. Context is not long-term memory. That means that if an application remembers something across requests, that information is stored outside of the model and deliberately brought into it later, right? That is why context engineering is more than just writing clever prompts. It's deciding what belongs in the current working state, what returns later, and what stays out. A model can produce an output, but that does not give it authority to change a file, call an API, or update application state. The application decides what input is allowed, when inference runs, how the output is shown, and what becomes permanent. The API is simply the interface between the application and the execution layer. It might be an SDK function, a worker boundary, or a local HTTP service. A tool is the capability the surrounding software exposes. So it can be read a file, search a database, call an API, or run a code. The model may produce a structured tool, but that does not mean the action already happened. The surrounding software still validates the request, checks permission, executes it, and returns the result. So when a model helps select tools and walks through multiple steps toward a goal, we often call this complete system an agent. A useful definition of an agent is a LLM that runs in a loop to achieve a goal. Sometimes they may have access to tools to do things in the real world, but that is completely optional. The machinery around what we just described is called the agent harness, right? It contains the loop, tools, permission, state, context, guardrails, and stop conditions. A coding harness can supply repository context, terminal, and editing tools, tests, permission checks, and a stop rule, which is what we see with VS Code, right? But a research harness can supply search, sources, citation rules, and an evidence threshold. A support harness can supply account lookup, refund tools, action limits, and human escalation tools. So same model, different harness, and different behavior. Autonomy describes how much of that workflow continues without asking a person. So it does not mean that the model become an independent being. So local tells you where inference happens. It does not automatically tell you whether the complete application is private, offline, or disconnected. A model may need network to be downloaded. That is distribution. Once present, inference may happen on the user's machine. That is local execution. Offline capable means the workflow continues without network after a dependency are present. Local first means the user controlled environment is the default, while an explicit remote path may still exist. A good friend Alex described local area as a stack. It is hardware, model, quantization, format, runtime, application, API, and sometimes an agent harness. Each layer affects the final experience. The photograph helps us understand the first half of that stack, the model as the asset, format as the way it is stored, quantization as the clearer and larger versus lighter and smaller trade-off, the runtime as the compatible software, and the backend as its parts to hardware. That is where the analogy stops. So from there on, we are describing the software system around the model. The application gives it a job, context controls what it can see, and the harness add tools and control action when the job requires them. So that is the lay of the land. You don't need to memorize every string term at once. Just ask where it belongs in the task. So is it describing the model itself, how the model is packaged, how it is executed, what it can see right now, what the application controls, or how much the NGSC surrounding the system has? Once you can answer that, AI stops looking like a magical box. It becomes software again. And that's exactly where episode 2 begins. I'm Daniel, and this is Bring AI Home. Thank you.